This mathematical adventure is being brought to you from Earth. The math wizard is eager to get to work today, so he calls in his new math apprentices, Vesace, and Thresh, and Itachi. Well, let's gaze into our mithril ball and see what calculus lore we can learn today. Indefinite integrals. Alright, so let's start off by doing a problem that we saw how to do just before the break, the integral from 4 to 5 of 3x squared dx. Now, don't forget what this actually represents. It's the area underneath the curve of y equals 3x squared. And we figure out that area between x equals 4 and x equals 5. Plugging this into our handy-dandy calculator, it tells us that the area is 61. But how would we get this without technology? Well, here's where the fundamental theorem of calculus can come to our rescue. So don't forget what FTC says. It says that if you're trying to find the area under the curve of a graph from A to B, actually, let me go back. So the integral from A to B of f prime of x dx is actually equal to f of b minus f of a. Now, how exactly does that help us here? And this is why I stumbled a second ago, is notice that after the integral sign, this graph that we're trying to find the area underneath, it's f prime of x, which means it's the derivative of some other function. And the function it's the derivative of, f, is what we need to compute the actual area. So if you go back to the original problem over here, we have the integral from 4 to 5, so that's going to be our a and our b, and the 3x squared right here. So the thing that we're trying to find the area of, that's actually our f prime. But what we need is the f to be able to figure out what the area is. So we need to ask ourselves, what is our f? What is this the f prime of? What is this the derivative of? Well, in this case, it's not too hard to see. If we take the derivative of x cubed, that's 3x squared. So that's actually exactly what we need here in this case. So the f of x is going to be x cubed, and we evaluate that. First we plug in this top number here, and then the bottom number. So we do 5 cubed, take away 4 cubed, 125 minus 64 is 61. And notice, hey, that exactly matches up with what the calculator had told us. Of course, it's perfectly fair to ask, how did we kind of come up with this x cubed in the first place from 3x squared? Well, I sort of thought backwards a little bit, and we'll talk more about that in a second. But one thing to keep in mind is that x cubed isn't the only possible answer. So there are other functions that if you take the derivative will also give you 3x squared, which is what we want. For example, what if we had taken the derivative of x cubed plus 10? Well, what's the derivative of x cubed plus 10? Well, it's also 3x squared, because the plus 10 just goes away when you take the derivative. So what if we had tried doing the problem with this as our f of x instead of this other one? Well, watch what happens. So we go ahead, and this time we're using x cubed plus 10, evaluating at 5, subtracting what we got at 4. So basically just using this part of FTC. So notice when you plug in 5, you do 125 plus 10 is 135. And then we subtract what we get when we plug in 4, which would be 54. And hey, that still comes out to be 61. Now, mathematically, you can kind of see exactly what's going on because the 2 plus 10s cancel. Don't forget that this minus distributed, that's what made it cancel there. In any case, this example was just to show that basically what FTC says is that integration, area under curve, is in essence kind of the reverse process of differentiation, the instantaneous rate of change. So finding out the antiderivative of something is actually really important to doing integration. And that's actually sort of the lead into something that's called indefinite integrals. Okay, so we're ready to introduce the concept of an indefinite integral. So suppose I write something like this, the integral of 3x squared dx. And notice I'm not giving you the bounds. I'm not saying 4 to 5. I'm just saying integral 3x squared dx. Well, if you see something like that, that's called an indefinite integral. And again, the key thing to notice here is that there's no bounds there on the integral, or what some teachers call the limits of the integral. I actually don't like to use the term limits, so we don't get confused with the actual LAM notation that we learned earlier at the start of the year, so I call them the bounds. So I left those blank. So that's where the 4 and the 5 were before. So we know that if I had written a 4 and a 5 there, that instead of an indefinite integral, it would be a definite integral. And we know what the answer to that is. We do the area under the curve from 4 to 5, and that's 61. But what in the world does this mean if there's no bounds? So if you have an indefinite integral, which basically looks like an integral symbol without the upper and lower bounds there, the numbers at the top and bottom of the symbol, what that actually means is it doesn't really mean do the area under the curve. So the answer isn't a number. So the integral symbol without the bounds, an indefinite integral, just basically means what's the antiderivative. So in this particular case, if we do the integral of 3x squared dx, we know an antiderivative for that is just x cubed. But it doesn't have to only just be x cubed, because we saw a second ago x cubed plus 10 works just as well. And why stop there? Why not x cubed plus 1,000? In fact, really, as we proved back first semester, any constant there can work. And in fact, every function that works is of that form. That's what we call the plus c lemma. That if you've got two different functions that both have the derivative of 3x squared, they just differ by a constant. So one way to express the general antiderivative is to say that the actual answer is just x cubed plus c, where c represents any constant. So it doesn't have to be an integer or positive or anything like that. Okay, but you still may be wondering, is there some sort of systematic way to have come up with that x cubed antiderivative in the first place? And in fact there is. So let's just kind of, again, go back to first semester and remind ourselves of the power rule. So remember what the power rule does. It gives us a nice fast way to take the derivative of polynomials. And it says that if you're taking the derivative of x to the n power, it's just n times x to the power of n minus 1. So basically the steps are to multiply by the exponent. Right, so here was our exponent right here, and to get the answer we multiplied by the exponent. But then the second step is to subtract 1 from whatever the exponent was. So before it was n, and now it's n minus 1. So in class, we sort of thought about that as like a Zelda video game, where you fall off the cliff and you lose a life. So here the exponent fell off the cliff, and then you lose a life. Go down a life because you fell off the cliff. Alright, well, now what we want to do, since we're doing antiderivatives, we need some sort of backwards power rule. So how are we going to do antiderivatives for polynomials? So in essence, what we need to do is reverse the process that we did for differentiation. So, and don't forget, if you've got a two-step process, so it's not enough to just reverse the order, you also have to reverse what the operations are. So in order to undo what we just did, we have to undo the second thing first. So rather than just subtracting 1 from the exponent, we're going to add 1 back to the exponent. And then we have to undo the very first thing we did, so that'll be our second step now. And instead of multiplying by the exponent, we're going to divide by that exponent. So let's take a look and see what this looks like for the problem we just did. So if we want to be able to find an antiderivative for 3x squared, what is it we need to do? So the way we would write this is we'd say the indefinite integral of 3x squared dx. And now let's just apply our backwards product rule. So we have to add 1 to the exponent. That's going to turn the 2 into a 3. And then we have to divide by that new exponent. So dividing by 3. And notice that, hey, those 3's cancel. and that's going to be our x cubed. But don't forget, whenever you do an indefinite integral, you have to add on that plus c. Now, that plus c has a special name, so it's called the constant of integration. So any time you do an indefinite integral and you express your answer, the antiderivative, you need to put that plus c on there, because it's not just one possible antiderivative. This represents the entire family of antiderivatives. That's all possible functions that, if you take the derivative of, give you 3x squared.